So next speaker is Professor Pinaki Mazumdar from University of Michigan. But before I introduce him, I'd like to add one comment. This engineering research center sponsored by National Science Foundation. It's called Biomimetic Microelectronics. So researchers at University of Southern California, they're trying to come up with a memory, implantable memory into human brain. It has been said that after age 17, your memory capability is less and less. So if we need implantable memory, flexible Memristor may be a good vehicle. That matches actually Leon's earlier talk. It's my great pleasure to introduce Professor Pinaki Mazumdar. I first met Pinaki when I was faculty member at Illinois. So we had 2 years of overlap between 1985 and 87. And I remember in one of the physical design courses, physical VLSI design course. In fact, where's the camera? I used to give always some lecture on Memristor. So Pinaki may remember my lecture on Memristor at that time. Since then, after graduation, he has done a lot. He was postdoctoral research at EECS at Berkeley, but for many years now, he has been at University of Michigan, Ann Arbor, as a professor in EECS department. For the last couple of years, he was a program director at NSF in charge of emerging technologies, actually. That's where he encouraged us to have a symposium on Memristor. So Pinaki made this all happen. So thank you, Pinaki.
Confused here.
When I was at Microsoft, they told me that no one there has ever used this.
I have not used this particular version of Windows.
Well, that's Vista.
Yep.
Where is that? Can I connect my computer? It's much easier. I don't know this particular version. is Memristor workshop. I have not used this particular version. Is the Memristor workshop? Oh, this. Okay, good. Yes.
Go down to the lower right.
Lower right here.
Lower right. No, that's the left. Go to the lower right.
Okay. And what is it?
No, I think you lost it. So,
Can you just put in
they're
the
over
slide?
there. Lower right. Click straight.
Oh yeah. Okay. Okay.
Yeah. They switched everything.
Yeah. So this is what happens if the technology changes so fast that we just don't know what to do, right?
So this is what happens when people are stupid to change the technology.
I think that's the concern many people have with this Memristor. If it comes too soon, then what will happen actually? So.
Can you put on the mic?
I'm sorry about that. I'm not familiar with this particular version of Windows. So. Well, I mean, I will just mention some of the applications that we are looking into at the University of Michigan. Professor Wei Lu, who is also attending this symposium, he is mostly responsible for fabricating all these things that I will show. So all the pretty pictures are due to him, and all these cloud shaping ideas are mostly because of me. So I'm in the CSC building, and he is in ECE, and we have an excellent fabrication facility in Lurie Nano Electronics Fabrication Lab, and that's where most of the fabrication that I will show over here has been done over there. Since my talk is at 2:30, and many of these things have been already covered by many people, Stan gave an excellent introduction to all these, so I will try to still just mention a little bit and then switch over to the main ideas. So as Stan mentioned that after Kirchhoff's applied the law of conservation of energy over an RLC circuit and related the four state variables with R, L, and C, for a long time, people really did not pay attention to this particular missing link over here. Of course, we know that due to Faraday's law, the other two arts are, the knowledge in the form of some electrical laws existed. So all of you know this. So basically, here the main concept is that unlike the other passive elements, here the device has some memory property, and that Professor Chua had noticed in 1971. Then, of course, over the course of time, there are a lot of work has been going on to produce that particular characteristics. Much of it has been done in industry, in different memory companies, because of the fact that this particular property can be taken advantage to make very high density memories, and most of it is in the secretive form. The university folks, they live on publishing. That's why we know this different work that has been done at various places in terms of the materials, combination, and their behavior. For memory application, off to on ratio, then data retention time, and how many times you can do the endurance and the energy consumption. These are the typical metric, and the different devices have shown different performance. This is the one that Wei Lu had fabricated at Michigan, and by far, amongst all these published ones, if you look into all the different parameters, this shows the superior performance. Basically, in this case, an amorphous silicon film is sandwiched between silver, metal, and polysilicon. Much of it is similar to the other types of structures that we have been hearing in the morning. In terms of on-to-off ratio, it could be, of course, tailored, higher than 10 to the power 4, and data retention time, several years, 10 to the power 7 seconds, and endurance is definitely better than many other devices over here, but it is not still to the extent that it could be, incorporated to replace DRAM or static RAM in cache, but it is good enough for flash memories, which has a huge market because of the portable electronics. The most importantly, the power consumption is very, very low. So both the integration density and the power consumption are the two different strong features of this particular technology. In terms of the view, this is the top view. You could see that the silver iron wires are over here, and then there's a thin film of amorphous silicon, and underneath you can see the polysilicon, and this is the side view where the silver and poly in between this amorphous silicon pillar is there. So as you have seen the illustrations in this particular thing, how the filament is formed because of the diffusion of silver iron in amorphous silicon, and depending on the voltage amplitude as well as the width, we see that to what extent the silver ion can assist the current flow so that the device can turn on and turn off. So this is the principle that we have been using. In terms of the device characteristics, these are some of the earlier designs which he had done of late. Because of some DARPA funding, he has improved the performance, but nevertheless, one can see the pinch of characteristics as well as some sort of signage type of growth of current, which is because of that you can get very fast switching time. So we have taken advantage of this to design both memories, digital memories, as well as some of the neuromorphic circuits, which I'll talk about. Now, often, people have been asking these questions that whether the physicists have been aware of the Memristor property. Actually, most of these calculations, I don't know how the name is missing, is due to Hill, who published a paper in Proceedings of Royal Society in 1969, almost the same time when Professor Chua had proposed this Memristor concept. And basically, by using the notion of the charge-assisted or the particle-assisted multiple tunneling barriers, and if you apply voltage, one can see that the current jumps in this form, that it just goes and sticks around in the particle, and then it jumps from one particle to another particle, and during that time we see some sort of a jump over here. And overall, the characteristics is very much similar to what people have used other types of modeling technique. So in 1969, what R.M. Hill had derived in terms of signage function, that still holds good actually. So in some sense, the notion of Memristor behavior of this, thin, when you apply voltage across a thin film was studied by the physicist. Similarly, the chemist, we know that, typically in sodium chloride solution, by applying voltage across some electrodes. So both the chemist and physicist did study this property, and after this 2009, when this has been connected to the Memristor work of Professor Chua, we can see now we are basically rediscovering the different things that are in the literature, and we can see that all of them kind of converge towards this particular new device, which is called Memristor. The biggest advantage is that, in addition to the fact that one can make the digital memories very densely, it also mimics the way the human brain works. Basically, as Professor Chua has shown, and this is the same picture over here, between the axon and dendrite. So the axon is the output of a neuron, and it goes to thousands of other neurons through this dendrite structure. So there is a membrane gap over which the neurotransmitters they move from axon to dendrite to provide the neurosignal. So we see that when there is a spike occurs, it goes up and then it goes below the threshold and then it comes back. So that particular concept is very much similar to the structure that we talk about. These ions could be considered as participants, the different types of neurotransmitting materials, and we can produce this type of spiking characteristics. And in terms of the equivalent circuit, you have seen in the morning that this is the equivalent circuit of Hodgkin-Huxley model, is very much similar to the Memristor equivalent circuit that we are using in most of our modeling and simulation activities, actually. The different things that I will talk about is pertaining to mostly the brain-like, computing or brain-like information processing. Basically, there is always this push for faster and faster technologies that has been accomplished by mostly shrinking of devices, and that's what we know as the Moore's law. But this trend is basically necessary in order to keep the economics moving. Over the past 100 years, that has been the trend as we move from electromechanical relays to vacuum tubes to transistors to integrated devices, and then probably much more denser form of information processing materials will be seeking, because ultimately, in order to compute as fast as in a complex way as the human brain does, we really require at least another 1,000 times improvement in terms of the processing power. The only problem is that even though the digital computers can accomplish that, but the power consumption associated with that will be of in the range of gigawatts, whereas the human brain, which consumes less than 50 watts. So there is a huge, difference in terms of the information processing capability versus the power requirement, and that's why there is a real push for non-digital computing, and most of it is in the form of brain-like computing. And I will mention a few different applications that we are looking into. These are very early form. I have only one student with whom I am working on this. One area of facets of brain-like computing is self-healing or robustness, as opposed to in digital computing. We know that even if a single bit is faulty, the whole system fails unless you use some sort of error correction or some other means of taking care of those type of sporadic faults. So this is an area where we see that the memristors can play some good role in order to improve the yield and robustness of the memristor memories. The other area, of course, is the spike-based, especially STDP-based learning mechanism, which is key at for most of the neuromorphic solutions. And we are introducing some of these things to some simpler circuits at this point. But DARPA has a big program, Synapse program, STAN as well as HRL and IBM. They are trying to develop much more complex systems, the behavior of a monkey or a cat. So I will mention a little bit because we have designed some circuit to that extent. And then my own work in the silicon memories, in different types of memories. As a result of that, we are also designed some memristor-based memories. So these are the few things I will quickly show to you. So this is what Wei Lu and his students, they have designed 1 kilobit crossbar memory, and then he had done some sort of studies in terms of the reproducibility of these memristive devices across 20 by 20 array. And what we see is that out of 400 cells, 31 of them have these defects, which are, in terms of the resistance, is way higher than the ones which you see in, these are the ones which are having resistance between 50 and 150 kilo ohms, and these brownish ones, the data is not written. So we can see that there is an 8% of defects. Of course, this is not really, you can characterize the whole technology by virtue of just one example like this, because this is an early stage in the lab. But this problem will be definitely persistently haunting this particular technology, that unless we have mechanisms to design circuits in the midst of multiple faults in terms of resiliency, we will have tremendous problem actually. And that's why we are looking into some of the ways to self-heal this type of circuit design. Now, I did quite a bit of work in coding theory earlier in the context of memories, but unfortunately, the different types of communication type of coding that we have the double bit error correction capability and all does not work out very good in the case of semiconductor memories, because of the fact that you have to do the decoding within one memory cycle time, which is 10 nanosecond. And many of these also use some sort of linear feedback shift registers, which are not also is compatible with respect to the memory pitch width and things like that. So earlier I designed some augmented product code to take care of some of the DRAM type of faults. But anyway, after doing all these things, I'm pretty convinced that this particular approach of applying error coding techniques, unless you are ready to sacrifice in terms of a huge amount of silicon overhead, it will be very difficult to do that, because of the fact that, as I showed, the types of the number of faults are very high. So the approach that we are taking is that we are representing the problem as a graph theoretic problem, as a vertex cover problem. So here are the so to start with, here is a 1 megabit memory. There are 1,000 rows and 1,000 rows and 1,000 columns. And say these dots are pertaining to the faulty rows and columns. Now, since we expect the density of failures is say 4 or 5% or less than that, so we would like to compact the fault. So in this row there are 2 faults. That's why 1001, and in this column there is only 2 faults. So this particular pattern represents this fault pattern which actually occurs in the physical memory. Then we will be using this fault pattern to internally repair the memory. Of course, if you apply for standalone chip, then of course you can extract this pattern outside and you can run this program in a computer, and then you can do in many ways to solve the problem. But we are talking about a scenario where this chip is embedded inside the larger application chip, so we have no means to extract out this fault and find out how to do that. So our only way to solve this problem is to create an intelligent hardware which would be able to very quickly find out where these faults are by asserting built-in self-test, and then using this built-in self-repair circuitry, it will be able to repair the chip actually. And that's what we have designed, and we basically given this larger array how we can create this compacted pattern. That's what is shown over here, which requires very little amount of extra overhead. Only we use some shift registers around the periphery. Now the way it works is like this, that we represent these faulty rows as one set of vertices and faulty columns as another set of vertices. And depending on where these faulty cells are, so each of these edges in this bipartite graph represent a faulty cell. So the goal will be to find a way to use the minimum number of spare, these rows and columns, such that we'll be able to cover all the faulty edges. And that's what is, in the graph theoretic term, is known as the vertex cover problem. Normally, the problem is very simple because it's a bipartite graph. You can run an order n square algorithm very quickly to find out that. But if you apply the restriction that I have only 2, say, spare rows and 2 spare columns, as the problem becomes more complex, it is known to be in the class of intractable problems, what is known as the NP-complete problem. So having said that, the biggest advantage in this particular approach is that we are trying to extract the global fault pattern, and then we are giving it to this intelligent hardware, which you don't know what it is like, and that intelligent hardware have the notion of the global faults, So it can always find out the best solution actually, and that's what we have shown. Now, what this hardware looks like is like this. Basically, we designed a neural circuit where these are the neurons over here pertaining to the rows and columns, and we have some multiplexers over here. So we know that if these neurons are connected through some programmable synapses, so if this synapse has the information about the fault in the memory, then we will be able to find out a good solution, and that's what we have demonstrated over here. So here is the fault pattern which I have shown over there. So now, actually it is a little different fault pattern, but in order to solve this fault pattern, the way the circuitry works is that we start from all the neurons from the ground state, and then we we basically program this Memristor such that this relates to the fault pattern over here. So we have the original fault pattern, and it's transposed over here because this part will be the interactions between row and column neuron and so on. So overall, we'll have these 4 quadrants. These 2 quadrants are not programmable. They are just having fixed weight for interactions. And in these 2 quadrants, we'll be programming the synapses, where the synapses will be programmed according to the fault pattern over here. Now, if we know that if we allow a nonlinear circuit like this by itself, it will try to minimize the Lyapunov energy function. And that Lyapunov energy function is expressed in terms of the state of the pre-neuron and post-neuron. So now the question is that what should be the synaptic values between the pre and post-neuron such that once the circuit stops working, it will find the solution if it exists actually. And that's what we have demonstrated, how to model the objective function of a combinatorial optimization problem like this, and how to find out in the transition matrix what these synaptic values are, and that's how the whole process is. Ultimately, when the circuit starts, then it just stops showing that R2 and C4, the neurons corresponding to that, will have the value. So R2 over here, so this will assume the value 1, and C4, this will assume the value 1. Now, since you see that C4 has got 3 faults and R2 has 3 faults, so obviously that's the correct way to solve. Even though for a simple problem you can intuitively justify that, but for a complex problem, for a larger circuit problem, this will be more difficult to do intuitively, but just to illustrate the principle. So basically that's what R2 and C4 are formed. Now after that, after these 2 solutions have been selected, we still see that these cells are not picked. They remain uncovered, and that's where so initially all of them start going down, but since the cost function has been selected such that it will push the energy function to be at the higher value until those faults are also covered, and then after some time R4 and C1 goes up, and then we have these 2. So finally we find out that using 2 rows and 2 columns, pair rows and pair columns corresponding to R2 C4 and R4 C1, we can actually make this memory chip faultless actually. So this is the idea that I believe is the most appropriate for this particular technology because of the fact that it's in its embryonic stage, and the aggressive scaling is really causing this type of problems, just not the, in case of way-loose measurements, you have seen that there is a huge amount of process scattering fault kind of thing. So that's how I believe that, the technique that we are developing will be very, very useful because of the fact that error correction technique really does not work out very well. Now, we also ran some statistics for different defect densities, for highly defect densities, without any error correction, or rather this, self-repair. the 20% is the yield, but as we increase the number of spare rows and spare columns, we can achieve 100% yield over here. Similarly, we also studied that what about if the neurons themselves are faulty, because the neurons are also made of some of the CMOS devices. So if they are faulty, or if some memristor, which is used as a synapse, if that has some catastrophic fault, like it is stuck to 0 or 1, or the bias generator which are needed for running this algorithm, they have fault. So we have studied all these things, and what is the best thing is that the memristors in the synapse, they are pretty robust, in the sense that even if 3 or 4 of them are faulty, still we can get the 100% best repair solution actually. So this is something we are pursuing as a way to improve the performance of the digital circuit, which will be definitely vulnerable when you introduce this type of aggressive technology. Now the second thing is that, as all of you know, that the work in the area of neuromorphic computing is as old as the digital computer itself. It started with in the 1960s with the perceptron work. The only problem was that in those days the amount of hardware required to do some of the simplistic operations were too high. So that's why most of the earlier generation perceptron work to recognize some alphabets and all did not go very far. Then in 1980s, John Hoffield had demonstrated how you can use the Hoffield type of network to solve traveling salesman problem in a silicon chip, and that required a few thousand transistors to do that. And then after that, there is a huge amount of evolution of different types of CMOS, AVLSI, analog VLSI chips, for emulating the performance of different parts of the the neuromorphic circuit elements, the soma, then axon, then dendrites, and so on. The real problem is that if you try to use the STTP learning model, which basically emulates the learning model of the human brain, the synapses become quite large. So that restricts that up to how many devices you can have in a realistic chip size actually, and that's mostly to the tune of few thousand neurons actually, and that's the main problem. Unless you have the huge amount of scaling, you really cannot demonstrate the real advantage of this particular technology, and that's where this Memristor technology has really provided a good avenue to solve that problem, because we can now replace this large number of transistors, the CMOS transistors, and we'll show in one of the applications that we have done about almost 1,000 times improvement in terms of the density of the chip actually. So this is the main goal of this particular studies that we are doing. Again, Wei has designed this type of analog type of memristive structure, which is very much similar to what Stan had talked about for his materials. I mean, he also has the different, doping regions. So the response is shown over here in terms of the number of operations, how the pinch loop, changes. So basically, we are trying to design some STDP-based circuitry, which will use with this type of memristor. Now, unlike in many of the analog circuits where you can use the amplitude of the signal to encode the information in terms of the synaptic learning, in this case, we have to keep the amplitude constant because of the fact that this whole thing is in the form of a crossbar, and we don't want to play with the amplitude on the crossbar itself as a to send the information. So we retain the amplitude constant, but we vary the pulse width. And again, Stan's group also have done a lot of work. We studied some of the work they did, and we used some of those, results that they have published. The advantage is that depending on the pulse width, you can vary the conductance in the memristor at different locations depending on the pulse width. So with this particular approach, we have basically designed our first chip. I don't know, how much time do I have? Oh, I'm already, okay. So what we can show is that, as Professor Chua and other people have shown, that we can get the STDP characteristics both in terms of the long-term potentiation and depression. Basically, that depends on the spiking, the temporal relationship between the pre and post neuron. If the pre-neuron fires before post-neuron, then we have this potentiation, and on the other case, we have the depression. And accordingly, you can see that here is the postsynaptic pulse, and depending on the occurrence of the presynaptic pulse, we'll have the positive learning, or in terms of the synaptic weights, it will change in the positive direction or in the negative direction. So with this, we have designed what is called the position detector. So if you have, this is a small example of 5 neurons in the sensing plane and 5 neurons at the output plane. So if the object is close to this neuron, corresponding to that, you can see that this neuron picks the signal, and you have the width of this shows the signal strength, and other neurons are almost 0, and this will directly transfer the information to this one. So the output will say that, okay, the position of the object is near this, and that's how this output is over here. But this works with any type of circuitry. You can use simple artificial neural net to do this, but the real problem is that if it is, so in the noise-free environment, it will work very well with any circuit. There is nothing magic about this. The real value of this circuit is that if it is in the background of a high noise, still this works, and whereas the other things won't work actually. And this is what we have demonstrated. And we have made the chip, and what we show is that there is almost 1,000 times improvement in terms of the density. And finally, we also made the memory because, as I mentioned, that our group have done a lot of work, so we are really interested, and we designed these things, and we have sent it out for fabrication. Now, Wei has to put the crossbar on 8 and show that 64 kilobit memory works according to our simulation and studies, okay? Again, there are efforts going on. I mean, this is from one of the presentations in that Singapore in a meeting that Steve have talked about. By stacking the memory, typically this cell size is 4f squared. So if you stack 8 bits, so you can reduce to half f squared. And there are some efforts in terms of having 4 pillars instead of single one. So you can see that up to 1.4 terabits we can use with this technique. And if we replace each of these Memristor cell with 4 of them, then we can go up to 8 terahertz, 8 terabit or so. Okay.
All right, thank you very much. So since we ran out of time, I think we can have maybe more conversation with Pinaki during the break. And I'd like to present the memory piece for your wonderful presentation. Thank you very much. Thank you. So before